This question comes courtesy of the Farticle Particle on Reddit. Do these two scenarios require the same amount of water pressure? Scenario 1. Pump water through a 3-meter vertical pipe and into the top of a tank. Scenario 2. Pump water into the bottom of a tank which already has 3 meters of water in it. I saw this question online and I remember asking this exact same question when I started working. So I thought, why not make a video out of it? Imagine you are swimming in a pool. We've all played all sorts of games where you go underwater and stuff around at the bottom of a pool. When you're submerged in the water, the weight of that water exerts a pressure on your body. Nothing special there, right? Now imagine that you go to the beach and you get into the water and you submerge yourself to a similar depth as you did in the pool. You don't think that just because there's more water in the sea that you're going to get crushed by the weight of all that water because you're in the sea and not in the pool. If you understand this explanation with the pool and the sea, then you already have a good understanding of this tank problem. It's just that your intuition might be a little bit different because it's not as if you're pumping water into tanks every day, necessarily. The intuition might be to think that it is more difficult to pump into the base of a tank because of the large amount of water that needs to be raised. Whereas if it's just going through a pipe on the outside, well then the weight of the water in that pipe is a lot less. But that intuition, it's incorrect. We use the term head as a way of expressing pressure. There's nothing too fancy about it, it's just instead of units like pascals, bar or pounds per square inch, we use meters, feet and inches instead. To convert a head into a pressure, all you need to do is multiply the head by the density of the fluid you're talking about, as well as the gravitational acceleration constant, which is roughly 10 meters per second squared. If you're thinking, actually it's 9.8 meters per second squared, get a life. So our 3 meters of water, which has a density of 1,000 kilograms per cubic meter, equates to roughly 30,000 pascals or 0.3 bar. If instead we had a 3-meter column of some random oil with a density of 700 kilograms per cubic meter, then the pressure exerted by that column would only be 21,000 pascals, or about 0.21 bar. Another example of where we use head is when we use mercury in barometers to measure atmospheric pressure. Atmospheric pressure is equivalent to 760 millimeters of mercury. Mercury is a really dense element at a density of 13,600 kilograms per cubic meter. Why are we talking about this? Well, have you noticed that in all of these examples of different head and pressure, we're only talking about the height of the column of the water or the oil or the mercury, not about the diameter of that column. If we were to increase the diameter of the column, yes, the total mass, weight, force of that fluid would be more, but so would the area over which that force is applied. Pressure is force divided by area, so the pressure at the base of any column of fluid doesn't change by making the column have a larger diameter. This idea is actually called Pascal's second law. It states that the pressure exerted by a column of fluid depends only on the height of that column of fluid and not on the amount. So a kilogram of water will exert a much higher pressure if it's contained in a long thin tube than if that same kilogram of water was simply sitting in a glass. There's actually a really great video called The Hydrostatic Paradox, which I'll link to in the description. You should really go check it out. They do a really good job of explaining this and also show how they are able to shatter a glass flask with a very small amount of water simply by raising that column of water to a height of roughly 23 meters. The reason that it isn't more difficult to pump a fluid into the bottom of the tank compared to simply up a pipe on the outside of the tank is because the heights of the fluid are identical. All the extra fluid in the tank is exerting its pressure on the base of the tank, which in turn causes the tank to exert pressure back on the fluid. So the tank provides the force necessary to support it. If we're pumping this fluid, it's not necessary for our pump to overcome anything extra in one situation over the other. Even if we took a tank with a conical base, it's not as if we're magically somehow funneling all the pressure onto our inlet pipe. The force on our inlet pipe is still the result of that same column of fluid. The rest of the fluid in the tank is exerting its pressure on the conical section of our tank. So apart from some minor changes in frictional losses because the piping arrangements are different in these scenarios, the real difference in pressure in getting that fluid into our tank is almost negligible. So you're not scared of swimming in the ocean as opposed to in a pool because there's more water in the ocean. And that's because most of the water in the ocean is not exerting its force onto your body, it's exerting pressure onto the ocean floor. In the same way, it's not more difficult to pump into the bottom of a tank because most of the fluid in that tank isn't exerting pressure on the inlet line, it's exerting pressure onto the base of the tank.